Buenos días. Muchas gracias por su asistencia el día de hoy. Antes de iniciar, voy a realizar una breve presentación del doctor Christof Steingass. El doctor Steingass es profesor asociado en el Departamento de Investigación de Bebidas de la Universidad de Geisenheim, Alemania. Las principales disciplinas en las que el doctor Steingass enfoca su investigación son la fitoquímica, la química analítica, la ciencia de los alimentos y de las plantas agrícolas. Realiza investigación sobre la caracterización físico-química de productos a base de plantas y sobre procesos tecnológicos de bebidas, por ejemplo, preservación térmica y no térmica, tecnología enzimática y técnicas de estabilización. Tiene experiencia en diversas tecnologías de análisis como la cromatografía de gases y líquida, además de espectroscopía de masas para análisis de compuestos bioactivos vegetales, incluidos los polifenoles y los carotenoides. El doctor Steingass nos hablará el día de hoy sobre el análisis de metabolitos secundarios bioactivos en frutas de Latinoamérica. Welcome.
So, thank you, Maria, for this kind introduction. I switched to English. I can understand Spanish, but I think it's better if I do the talk in English. So it's a pleasure to give this presentation today about the analysis of bioactive secondary plant metabolites in Latin American fruits. But I also would like to take the opportunity to present our university, because does anybody know Geisenheim University? So this is what I expected. So in the beginning, I would like to briefly introduce Geisenheim University. We are located in the southwest of Germany, close to Frankfurt. This is the biggest city nearby, and Geisenheim University is located in Geisenheim, a comparatively small village in a wine-growing region. And here you can see, for instance, the River Rhine and the vineyards in Rüdesheim, that is very close to Geisenheim. And we are located close to the upper middle Rhine Valley. It's called, this is a UNESCO World Heritage. So we're close to the bigger cities like Frankfurt, but it's still a quite calm region. But as you can see, it's a wine growing region, and this is also one of the main topics at our university. We have less than 2,000 students, so this is very small, but as I said, we are very focused on wine and beverage production and research. We have 44 professors, 48 scientists, and approximately 350 administrative and technical staff. We have 18 degree programs, so if you're interested, 8 bachelor and 10 master programs. If you're interested in these programs, you can check on the website. Internationalization is very important for us. We have, even we are small, we have lots of collaborations, approximately 160 cooperations with partner universities and research institutions. And since end of last year, now we have a cooperation agreement for student and faculty exchange, and I'm very happy that we can start. Now we have the basis to start a collaboration with UCR. Geisenheim University goes back to a research institution, the Royal Academy for Fruit and Wine Production, that was funded in 1872, and this research institution was converted to a university in 2013. And the main focus is plant food production and processing, mainly in the area of œnology and beverage technology. I am working at the Department of Beverage Research, and the head of the department is Professor Ralf Schweigert. I suppose many of you know him, because he has also a very strong connection to Costa Rica and to Patricia and Victor. Currently, he is the head of the Department of Beverage Research, and he holds the chair Analysis and Technology of Plant-Based Food, and this is basically what we do. So currently we have 2 senior researchers, 1 engineer, and 8 PhD students and PhD students and additionally 15 staff members. In our department, we have 3 additional professors, but they are mainly focusing on teaching. This is a kind of teaching professorship, and we're focused on both teaching and research. What are the activities at our department? We focus on the technology of plant-based food and also on the analysis. And so we have strong collaborations also with the plant breeding departments at our institution. With plant cultivation, we have lots of projects also going in the direction of nutrition and health. For instance, we have a project, an ongoing project about the impact of phenolic compounds in orange juice, how they affect human health. And also one big topic is authentication of foodstuff, mainly beverages. And for all, we are equipped with liquid chromatography. We have a comparatively new UHPLC ion mobility spectrometry, Q-TOF high resolution MS, and an ion trap LC-MS, in addition to gas chromatography, GC-MS mainly, spectroscopy, so 1H NMR, and we use the 1H NMR mainly for quantitation purposes, not for structure elucidation. We have UV-Vis and FTIR spectroscopy, elemental analytics we do with ICP-MS, AAS, TXRF, and we have several additional methods, but we also do classical wet chemical analysis that is very important in wine chemistry. And in my responsibility at the department are mainly the chromatographic and mass spectrometric methods. So I had to remember when did I start working with tropical fruit, and it was as early as 2009 when I did my diploma thesis about carotenoids in papaya, and this was the first time when I came to Costa Rica. And since then we have been working a lot with diverse tropical fruits, for instance palm fruit, American oil palm, African oil palm, viscoyol, macaúba, pineapple, nance, papaya, and I will give some information. I cannot present everything that we did in these 13 years, but I will focus on these palm fruits and pineapple and papaya, and mainly on the carotenoids and tocopherols, as well as some phenolic compounds. We did a lots of work on the characterization on these functional constituents, and we wanted to investigate the impact of pre- and post-harvest procedures on the concentrations and composition of these secondary plant metabolites. And we analyzed the phytochemical profiles. We did a lots of work on the identification, which compounds are contained in the individual fruits. And we also did some investigations into the bioaccessibility and bioavailability of especially carotenoids. Why are carotenoids so important, or are still so important for our research? What are carotenoids? Carotenoids are lipophilic natural colorants. They are the second most abundant pigments in nature after chlorophylls, and they give the yellow, orange, and red color to diverse fruits, vegetables, and petals. They are only synthesized by plants, algae, bacteria, and fungi, so higher organisms like animals and also humans, they have to uptake them with the diet. They are bioactive. What is the bioactivity and functionality of carotenoids? They are antioxidants, and there are hundreds of studies that established relationships between the prevention of diverse diseases and the intake of carotenoids, for instance lycopene. You can find carotenoids like lutein also in the human eye. This is for photoprotection of the tissue. And the most important function of the carotenoids is the provitamin A activity. Some carotenoids, if they carry an unsubstituted beta ring, they can be converted into vitamin A. And vitamin A is still a very important issue. It's a global dietary problem. this is a quite old number, but the situation has not changed that much during the past years. So there are many children, preschool children, affected by vitamin A deficiency, especially here in Africa, in African regions, but also in some countries that you would maybe not expect that they have an issue with vitamin A supply. Vitamin A is involved in vision, in growth and development, immune defense and reproduction, and if a person is suffering from vitamin A deficit, this will result in an increased morbidity and mortality, but also may result in for instance, in night blindness. And as plant foodstuff is available in most regions in comparison to animal derived products that are quite expensive and in some instances not accessible for the population, it's still very important to find good plant sources that contain provitamin A carotenoids. One of our projects that we did together here with the UCR was to characterize Acrocomia aculeata, the macauba palm, as a sustainable lipid source. And why is this important? I don't know if it's still a topic here in Costa Rica, if it's still in the media. In Germany now there were lots of reports about the impact of oil palm cultivation in Southeast Asia, but I mean now everybody's talking about the war in Ukraine, so this is not in the media anymore, but I'm sure it will pop up again in a couple of years. The oil palm oil is the most important source for edible vegetable oil, and approximately 65 million tons are being produced every year. And the big drawbacks of the oil palm cultivation, especially in Southeast Asia, is that there are extensive monocultures where you just can see Elais guinensis, so the African oil palm, and you know this is highly susceptible for phytopathogens, resulting in an extensive use of pesticides. Here you can see this. I don't know, have you seen this picture before? These are the palm oil survivors. This photo won the Photojournalist Award in 2017. So in these days, this was really a hot topic. Now it's not at the main focus at the moment. But why is palm oil so important? It finds a broad range of applications, both as feed, food, and also in the cosmetics industry. The fat yields of the fruit are very high, so up to 70% of the dry matter contains lipids. The lipids that you can extract from the fruit have a high melting point, rendering them very interesting for certain applications in the food industry. And you can obtain lipid fractions from the kernel, so the kernel fat and the mesocarp oil, but also carotenoids that are used as natural colorants in the food industry. And the crude palm oil can be considered as a functional food as it contains high levels of vitamin E, carotenoids, and, for instance, squalene. So we were looking for alternative plant sources that can compete with the oil palm but are more sustainable. And we found this very, very interesting plant or palm, Acrocomia aculeata, the macauba, or I think here in Costa Rica it's called coyol, right? And this plant has its origin in Central to South America. And the big advantage of this palm is that you can also cultivate it in temperate zones, not only in the tropical regions as applies for the African oil palm. The yields that you can achieve with this oil palm are even higher than those that you can achieve with the African oil palm. So it's really a promising lipid source. And the idea would be to cultivate this plant on existing grassland. For instance, this is a picture in Paraguay. So you can have a double use of the same area. You can keep cattle and you can produce palm oil in a sustainable way. We did a lots of work to compare, to characterize the lipids, also the prevailing triglycerides, triacylglycerols, and the fatty acids. And as you can see, for comparison, we also analyzed African oil palm, American oil palm samples, and also interspecific hybrids. And if you compare for instance, the lipid contents, you have to take into consideration that these are already selected lines that we obtained from a commercial breeder, and these results were obtained just with wild-growing Macaúba palms. And you can see that the mesocarp lipids the content is not that high, but for instance, if you look at the kernel, that is also a very important product. You can see that even the wild-growing Acocomia plants can compete with the African and the American oil palm as a lipid source. And also the composition is quite similar. You find higher proportions of unsaturated fatty acid in the mesocarp oil and high proportions of saturated fatty acids, mainly C12, 14, and C16 fatty acids in the kernel. And this is a composition that resembles that of the the kernel fat of the African oil palm and also coconut, for instance. We did a lot of work also on the characterization of the triacylglycerols, and you can see this is a mesocarp oil and a kernel fat, a quite complex profile of triacylglycerols, but they determine the technological properties of the oil and the fat, such as the melting point, so it's very important also to know these profiles. But today I will not focus a lot on the major lipids, more on the minor lipids, the carotenoids and tocopherols in these palm species. And here, these were our first samples that we collected here in Costa Rica. And we characterized the carotenoids and xanthophylls in the mesocarp during fruit development from green early maturity stages to the fully ripe palm fruit. And if you look at the chromatogram, I don't want to go that much into detail, but what you can see is that the Macaúba contains a very, very complex carotenoid profile with a lot of different xanthophylls, so the polar early eluting compounds. Here, carotenes, beta-carotene as the prevailing carotene, so a carotenoid that does not carry oxygen in the molecular structure. And this is the most important precursor for vitamin A. But we also found comparatively high levels of phytoin and phytofluin, and those are the early precursors in the carotenoid biosynthesis that are not yet colored, but there are lots of papers now coming up that also assume that these are also highly bioactive, but they have not been studied in detail because most of the research during the past decades has been done on the colored carotenoids because you can see them and you can easily find them. But this would be my recommendation when you do carotenoid analysis. You may always focus, also you have just to record in the UV range at 350 and 290 nanometers, and then you will also see these colorless precursors like phytoin and phytofluin. The method that we established here was quite nice because we were also, it also permitted to simultaneously quantify tocopherols separated on a C13 phase, and we coupled the DAD and the FLD in series, so we were able to quantify both vitamin A, carotenoids, and tocopherols, and this worked quite well. So if you have a look at the carotenoids in these maturity stages, we found mainly the xanthophylls that are possibly involved in the xanthophyll cycle, so the scavenging of light intensity, violaxanthine, anthraxanthine, and zeaxanthine, then the carotenes, beta-carotene, and comparatively high levels of these colorless carotenoid precursors, phytofluin and phytoin. And as you can see in the chromatogram, there are also a lot of geometrical isomers of the carotenoids present in the fruit, and we assume that this is due to the isomerization in this lipid matrix, the palm fruit. So we also compared the total levels in the mesocarp and the shell, the exocarp, and what is also quite interesting, the carotenoid levels in the edible fraction, so the mesocarp, they are already considered as high according to this classification proposed by George Britton. But if you look at the exocarp, the levels clearly exceed those that you can find in the mesocarp fraction. So this could also be an interesting source for carotenoids, maybe for the use in animal nutrition, for instance. But those are some preliminary results. If you have this chromatogram of the Costa Rican samples in mind, this is what you see here, and we received some additional Acocomia samples from Paraguay, but we don't know exactly, not for all samples, we know their exact origin, so it's for a publication, it's difficult to use it, but still we analyze them, and what you can see here, that there are some samples that have also, even the samples in Costa Rica, they had approximately 800 micrograms per 100 gram of fresh weight total carotenoids, and there are some samples that clearly exceed those contents that are already comparatively high. So, and what we also recognize, there are some chemotypes that have high levels of carotenoids, xanthophylls, mainly xanthophylls, but very low concentrations of beta-carotene, and others, they have really high levels of beta-carotene, so resulting in high levels of retinoic acid equivalents. And what was also very interesting for us to see, also in the tocopherols, we found very different composition. I mean, we just analyzed 5 different accessions, and we found some samples that predominantly contained alpha tocopherol, and some others contained beta tocotrienol and delta tocopherol. And I think also Andrea did a lot of work on the vitamin E profiles. So, but I think there's still the need to do further studies in the characterization and the selection of suitable accessions that can be used for industrialization. Another palm fruit that we investigated was Viscoiol, Bactris guinensis, and this is also distributed from Nicaragua down to northern Colombia and Venezuela, mainly in the tropical zones, and it's growing in seasonally dry and humid forests. And here, do you have any products on the market here in Costa Rica that contain Viscoiol? Also, they are not available, I suppose, not yet. Also in Europe, I have not seen any beverage, for instance, that contains Viscoiol. So it's really an underutilized crop, but that has a huge potential for industrial exploitation. And we collected some wild growing samples in Llano del Cortes, in Guanacaste, and we did a characterization of the micronutrients. If you look at the flesh, it does not look very orange or red, but still we wanted to have a look if there are, we assume that there are maybe carotenoids present, and we analyzed the carotenoids, and we were quite surprised because this fruit contains quite high carotenoid levels, even if they are not visible due to the anthocyanins that cover the color of the orange color of the carotenoids. And the most abundant carotenoid was beta-carotene, so the most important vitamin E precursor. So this is a quite nice source also for vitamin A or provitamin A. And the edible flesh also contained tocopherols, mainly alpha tocopherol. And we used here the same method that we used for the Acocomia samples. But we also wanted to look more into the composition of the phenolic compounds. And what you can see here, these black colored fruits, they contain anthocyanins, we recorded the anthocyanins using a different method, so you cannot compare the retention times. But the most abundant carotenoid was cyanidine rutinoside. And we found lots of different compounds, other phenolic compounds, mainly flavan triols, oligomeric proanthocyanidins, flavonol O-glucosides, and flavon C-glucosides, in addition to phenolic acids. And we read in literature that some palm species also contain insoluble bound phenolic compounds, so we also had a look at the insoluble bound phenolics in this fruit, and we were again surprised a little bit because we found comparatively higher levels of coumaric acid, ferulic acid, and also hydroxybenzoic acid. But you have to do an alkaline saponification of the cell wall bound phenolics, and then you can also quantify them with HPLC, and I think you do this here at CIGRAS also with grains, for instance. So it's also always good to have a look at, we try to characterize a broader range of phenolic compounds in this fruit, and we were quite enthusiastic to find such a broad range of different phenolics. But it's also worth mentioning that the kernel contains approximately 35% fat in the dry matter, and this renders the kernel an interesting source also to produce edible fat. And the composition was very similar to that of coconut and palm kernel. So when we look at the composition and the quantitative levels of the polyphenols in the Bactis guinensis fruit, the most abundant compounds are anthocyanins and flavan triols and oligomeric procyanidins. Here you can see the structures of these compounds. We found monomeric flavan triols, but also oligomeric compounds. And what is quite interesting, if we think about the bioactivity of such polyphenols, I think it's well known that red wine consumption also has health benefits, or may have health benefits owing to the anthocyanins, amongst others. But there's now a health claim for cacao flavonols in Europe, and I don't know if this is well known here, but I was surprised to see that this is one of the first health claims that we have for phenolic compounds in Europe. And so the claim is that cacao flavonols may help to maintain endothelium-dependent vasodilation, which contributes to healthy blood flow. But you can just use this health claim if you consume 200 milligrams of flavonols per day, and the degree of polymerization should be less than 10 subunits. You can see here the structure of such an oligomeric proanthocyanidin. And we found these compounds also in Bactis guinensis, so this is also a quite interesting source for flavan triols and their polymers. And it's worth mentioning here that with this reversed phase C18 chromatography, we just can quantify the OPCs up to a polymerization degree of 4. So we assume that there are also bigger polymers present, but then you should use another chromatographic method. So this is a very interesting source. And what we recognized when you compare the composition of Bactis guinensis, for instance, to acai, that is, we saw that it's very similar. We have similar phenolic compounds, the same prevailing anthocyanins, and acai, at least in Europe, is very popular at the moment. You can see, for instance, here the vitality bomb from South America, and also these acai bowls are very popular. If you check this in the internet, you find hundreds of pictures, and I was a little bit surprised. And acai, I think they have a very good marketing behind this, but I think Viscoyol has the same potential, but it's not promoted at the moment. And you can find lots of smoothies, and in Germany, for instance, you can buy frozen acai puree to make these acai bowls. And So the next plant or fruit that I investigated a lot during the past more or less 10 years is pineapple, that also originates from South America. I mean, nowadays it's distributed worldwide in tropical and subtropical regions. It's used for fresh consumption to produce canned pineapple and also juices. And one of the most important quality determining parameters is the color of the pineapple flesh. And this applies for both the fresh fruit and also for the juice. So I was a little bit surprised when I started my PhD thesis. I mainly worked with aroma compounds of pineapple, and I was a little bit frustrated because I recognized the first publication about pineapple volatiles was from 1945. And so I did a literature survey, and I recognized there are hundreds of papers almost about pineapple volatiles. And then I recognized, okay, I did lots of carotenoid analysis. I will also look for carotenoids in pineapple, and there was almost nothing. And this is very interesting because it's one of the most important targets for breeding is the sugar level of the fruit, the storability, that you can export it by sea freight also to other countries like Europe, and the color of the flesh. And also for pineapple juice, the European Union is one of the biggest markets for pineapple juice. So more than 50% of the total world production of pineapple juice is imported to Europe, mainly from Costa Rica and Thailand. And they have a share of 80% of the total EU market for pineapple juice. And according to our legislation, in Europe, juice is the fermentable but unfermented product obtained from fruit, having characteristic color, flavor, and taste typical of the fruit from which it comes. And when you process pineapple, there are two important things to know. Many pineapples are processed, so approximately 50% of the fruit, if you do an industrial processing, is the edible flesh, and this is mainly used for canning, and then you can sell the canned flesh. And so all these cut-offs and trimmings, they are used sometimes for producing a kind of milk juice, so they are homogenized and the juice is extracted, and this is used as a syrup during canning. And large quantities of byproducts that emerge are used to produce pineapple juice. But if you keep this in mind, that it should be obtained, if you look at the Codex Alimentarius, it should be obtained from the flesh or parts of the flesh and not of the shell. And so this is a very big issue in Germany or in Europe in general. There are possibilities of adulteration where you admix these shell or peel extracts to a real pineapple juice. And you should keep in mind that the juice should have the same color as the fruit where it comes from, because this is very important for pineapple processing. I will show you an example later. So what we did, we wanted to see if it's possible to distinguish these juices that are obtained from the shell and those that are obtained from pure flesh, and we used different maturity stages or post-harvest maturity stages to cover a broader range, because maturation has a big impact on the composition of pineapple. And we used the pulp, and we extracted the juice using a food mill, and we used the peel that was pressed directly. This is something that is maybe still a juice, because you obtain the juice by pressing mainly from the flesh adhered to the shell. And we homogenized the peel, and we obtained a kind of milk juice. And we pasteurized all the juices, and we did an analytical characterization, so some basic parameters like soluble solids and so on. And we analyzed the phenolic metabolites because we knew from previous studies that there are specific compounds that are mainly present in the outer fraction of the fruit. And it's very interesting which compounds you can find in pineapple, because for these 3 compounds here, some of the most abundant compounds are some phenolics that only exist in pineapple. They are known in not any other fruit on the world, and this is for instance this S-synapyl glutathione. That is a very unique constituent. And we found some, or a broad range of different compounds. You can see this is always this, these residues, this coumaryl, coniferyl, and synapyl residues that are attached via a sulfur bridge to cysteine, gamma-glutamyl cysteine, or glutathione. And this is obviously quite nice to authenticate pineapple juice, because you will not find these compounds in any other fruits. But we also wanted to see if we can discriminate juices from the outer fraction and the shell. And also we found some phenolic esters, so esters of caffeic and paracumaric acid with isocitric acid, and they are also known just in a very few plants, mainly, for instance, I think in grasses they are known. And this is interesting because pineapple is also a monocotyledonous plant, like grasses. And so this is also a very suitable marker for authentication of pineapple products or pineapple juice. And just as a side notice, they can be very easily confused with chlorogenic acids because they have almost the same mass and a similar mass fragmentation. But to distinguish them, you can use, for instance, high resolution MS, or you can compare the MS fragmentation with the known chlorogenic acids. So in total, we found, we did the quantitation with UV, and we were able to quantify some amino acids, biogenic amines, serotonin, these furanones that are also some quite interesting compounds. So we had in mind to analyze phenolics, but we found some additional compounds that you can easily quantify by UV detection. And those, this is the abbreviation for hydroxydimethylfuranone, HDMF, and methoxydimethylfuranone, and here you can see the structures. And those compounds are very important aroma compounds of pineapple, and they are also found, for instance, in strawberries and other berries, raspberries. And so we were able to quantify them in parallel. Then we found these 7 coumaryl, coniferyl, and synapyl derivatives that I've shown before, the phenolic esters, and some further phenolic compounds, mainly some glucosides of phenolic acids and a phenolic amide. So we quantified all these compounds in these different juices and calculated a principal component analysis, and what you can see that we get a really nice separation of the samples that were extracted from the pulp, irrespective of the maturity stage, and we get a second cluster containing all the peel-derived juices. So this was quite nice to show that we can really distinguish genuine pineapple juice from the peel extracts. So, as I said in the introduction, pineapple, the color is very important, and so we also studied the carotenoids in the pineapple flesh, and we saw a quite complex profile of carotenoids. And as an initial step, we assumed, because they eluted very late, we assumed that they are maybe xanthophyll esters, so we did an alkaline hydrolysis, and then you cleave all these esters and you just obtain the xanthophylls, and the most abundant pigments were LE and 9Z violaxanthine, and here beta-carotene. To identify the individual xanthophyll esters, you can use HPLC coupled to APCI mass spectrometry, and this is an example for the fragments that you can see. They are basically the same that you can see when doing MS experiments of xanthophylls. So elimination of water, and from this polyene chain of the carotenoid you have the elimination of toluene. But as a distinctive feature, you have a neutral loss of the fatty acid that is attached on one of the hydroxy groups of violaxanthine, and then you can identify the xanthophyll esters, here the example of the most abundant one, 9-Z-violaxanthine laurate. And this is also quite interesting for authentication because, for instance, citrus juices can be differentiated using the xanthophyll esters. You find, for instance, cryptoxanthine esters in mandarins that are not present in orange juice, and so you can easily prove the admixture of different citrus species. And we were quite surprised because this was the first report on xanthophyll esters in pineapple. And we compared different varieties. The most important one in international trade, and I think also here in Costa Rica, is this MD2 that is often sold as extra sweet or golden. And we found total carotenoid levels of approximately 300 micrograms per 100 gram. And the levels are not that high. They are to be considered as low to moderate compared to other fruits, but still, as I mentioned, the color is one of the most important features that have an impact on the consumer acceptance of fresh pineapples. And what we did in Geisenheim, we processed pineapples into a direct juice using a conventional rack and cloth press. And what you can see is that the color completely disappears. And if you keep in mind the legislation that a juice should have the same color as the fruit, this is questionable if this is really a pineapple juice. And we use a comparatively new device. These are just some preliminary experiments or ongoing experiments that we do. This permits juice extraction under complete oxygen exclusion, and then you can see that you really retain this intensely yellow color of the pineapple in the juice, and so we are still working on that. So, and the end of this presentation, I will go back to my very first experiments or contacts with tropical fruit on a scientific level, papaya. It also originates from Central America, so you can also find wild-growing papaya fruit here in this region. And they are really nice sources for micronutrients, such as carotenoids, but also vitamin C. And we did a characterization of yellow and red-fleshed chemotypes. And this is the main difference between the red ones and the yellowish ones is the presence of lycopene, so the same carotenoid that you find in tomato fruit, for instance. And also most of the remaining pigments that you can find are vitamin A precursors, such as cryptoxanthine, and you also find fatty acid esters of cryptoxanthine, free cryptoxanthine, and beta-carotene. So it's a really nice source containing both lycopene, like tomatoes, and mainly vitamin A carotenoids or provitamin A carotenoids. And we did a characterization. I will not go that much into detail, but we characterized these papayas here that you can see, diverse. They differed largely in the size. We had these very small Hawaiian pineapples and also very big ones. And I did not find this picture anymore, but one of them was like this. But it's mentioned this picture. And but as a take-home message, all papayas that we characterized had really, really high carotenoid levels, and compared to other fruits that we characterized or compared to literature. We also did some studies into the deposition forms of the carotenoids in different plant sources, and what you can see here are the chromoplasts that you can find in carrot root, tomato, compared to those that you find in mango and papaya fruit. And we did experiments on the bioaccessibility. This means the liberation and micellularization in an in vitro model. And this gives you a first hint on the bioavailability, because just the fraction that is liberated from the food matrix will be available for absorption. And we did we wanted to establish a relationship between the chromoplast structure and the bioaccessibility and also the bioavailability of the carotenoids. And what you can see here, in carrots and tomato, you find very large crystals. And if you compare this to the small structures in papaya, you can think about the solubilization of the carotenoids. If you have a big carotenoid crystal, this is hardly soluble during digestion compared to very small crystals or maybe even other deposition forms. And to get a deeper insight into the deposition form, we compared chromoplasts, the ultrastructure of the chromoplasts in yellow and red papaya fruit. And what you can see here in the yellow ones, you just can see some globular structures. And we assume that these globular structures contain, and also these tubular ones contain, lipid dissolved and liquid crystalline beta-carotene and cryptoxanthine, so the cryptoxanthine esters mainly. And the red ones had a very similar ultrastructure, but in addition you can see these membrane remnants, and they are very typical for carotenoids that are deposited in a crystalline state, because the crystals are covered by a membrane, and during the sample preparation, the fixation, the carotenoids are washed out, and you see, instead of the crystal, you see these membrane remnants. And so we assume that by comparing these two ultrastructures, we assume that the lycopene is also deposited in a crystalline form, but in very small crystals compared to the deposition in tomato fruit. This is just to complete the picture, the carrot root crystals, and you can see also these remnants of the solid beta-carotene, the prevailing carotenoid in tomato, in carrot root. And here in tomato you see this crystal and also the crystal remnants of the large lycopene crystals that you find in the chromoblasts of tomato. And this was the target of all our investigations, and to be honest, I was not involved in this study anymore, but this was, I think, the proof of our hypothesis that the deposition form in the chromoplast has a large impact on the bioavailability, because what you can see here is the bioavailability after consuming 13 milligrams of lycopene from tomato and papaya. And what you can see here, the response in the plasma, so this curve is the plasma level of the carotenoids in papaya, was approximately 2.6-fold higher than that of tomato, and the same can be seen for beta-carotene from papaya compared to tomato and carrot. So to summarize a little bit what we did and during the past years, macaoba can be considered as a really sustainable alternative to the oil palm, and there's a huge diversity in Latin America that merits further investigation. Viscoliol is a very promising source of vitamin A, as well as proanthocyanidins and anthocyanins, and it's quite interesting raw material for value-added processing to obtain, for instance, coloring foodstuffs, but also functional beverages, dietary supplements, and so on. Pineapple we were able to do the first report of violaxanthine esters in pineapple, but this is interesting for the fresh fruit, but during processing using conventional technologies, you will always lose these colorants. So there's a huge potential to develop novel processing strategies to also retain this pleasant yellowish color of the pineapple flesh. And I think this also applies for papaya. I don't know if you ever have produced a papaya puree. This quite pleasant flowery flavor will disappear when you use a normal processing. So here there's also a huge potential to further improve the processing strategies in order to obtain products with superior sensory quality and to retain all these carotenoids and vitamins that are contained in papaya fruit. And I would like to give you a brief outlook what we are currently doing. So we still collaborate quite intense, and I'm very happy that we can continue this collaboration that has been established between Hohenheim and UCR, that we continue with this collaboration together with Geisenheim University. And we are currently working on characterization of anthocyanins in Tradescantia species. We do a joint project about the use of quantitative 1H NMR to characterize Costa Rican foodstuff, beverages, and fruits. And we work together on the processing of tropical fruit under low oxygen conditions with the spiral filter press that I mentioned. And I'm looking forward to resume the work on bioactive constituents in coffee in the, I think, very near future. So I would like to thank especially Patricia, Victor, and Maria for the invitation and for giving me the opportunity to do this presentation today. And I would also like to thank all my colleagues at Geisenheim University and my former colleagues in Hohenheim, and also all the industry partners that supported us during the past years. And what you can see here, this is a compilation of all the institutions that supported our exchange. And you can imagine almost 12 years of exchange from both sides. Every exchange means normally you have to apply for a scholarship. And so we have a really huge we had a broad range of supporters during the past 12 years and rendering this collaboration possible. And I would like to thank you for your attention with this picture of a pineapple flower growing in Germany. So, thank you.
So thank you for your nice presentation. Ahora vamos a entrar al periodo de preguntas. Si alguno tiene preguntas para el doctor Steingass. Puede ser en español y yo lo puedo traducir. O en alemán.
A ver, María, traduzca María. You mentioned the colorless carotenoids, which could be precursors of other forms that have shown to be interested for human health or functional issues, phytoin and phytofluin. Besides being precursors, there's already some insight about direct effects on health or on some health-related properties?
I think the effects are not that well studied compared, for instance, to lycopene or beta-carotene, but there are some emerging reviews about this topic. And what was interesting for us, normally you can find them in lycopene-containing plants like tomato or watermelon. When you have these acyclic forms of carotenoids, then this is an indication that they may also contain these colorless precursors. But this was interesting for Acocomia because we found these colorless precursors, but almost no lycopene. So it's also something unique, I think. And there are also studies out there that report a comparatively high plasma level of these colorless precursors, but their function are not really known. so far. But I think this will be one topic that the Carotenoid Society will focus in the next years.
Thank you very much for the presentation. My question is regarding the analysis of phenolic compounds in pineapples. Did you have any significant difference of phenolic compounds concentration between the different maturities of pineapples? And which one was the most important phenolic compound? Thanks.
There were some, the phenolic compounds, there were not that big differences between the maturity stages, but what we observed, these furanones that I have shown you, this HDMF and MDMF, this really increased with progressing storage duration, indicating that the flavor develops during post-harvest storage. The stages that we analyzed were just post-harvest samples. The profile of phenolic compounds was more or less stable, but there was still a difference between the outer fraction and the edible flesh.
Regarding this, I don't remember if you show if there was a difference between the fresh fruit, the polyphenol profile from the fresh fruit and the juices from...
We just compared the juices.
Okay, only the juices.
Yeah, only the juices.
But is suspected that there will be a difference between
they
juices
are
and fresh fruit?
comparatively stable. These glutathione derivatives or conjugates, they are comparatively stable. So they also are present in the fresh fruit and after processing. But what is also worth mentioning for these glutathione conjugates is that they are efficient inhibitors of enzymatic browning reactions, and there's a patent for the use of these phenolic compounds to prevent browning of, for instance, apple slices and so on. But also here, there's almost nothing known about the bioactivity. I mean, glutathione is a very important antioxidant, and it's a combination of glutathione and a phenolic compound that is most likely very interesting with regard to the bioactivity, but it's not yet studied.
Okay, thank you. ¿Más preguntas? I have one question about the Bactris guinensis. The polyphenol profile, do you have the whole polyphenol profile of the fruit, or only these ones that you show us, like the anthocyanins and this kind of polyphenols?
We just have the results that I've shown you. Okay. We did not do the analysis of the polymeric proanthocyanidins. Mm-hmm. This would also be worth of investigating. What we did, we compared, I mean, this was just one accession, and we analyzed the phenolic profile in the edible flesh and also the peel, and then we calculated the concentrations in the edible fraction. But also the kernel is, it's known from other palm fruits that they also contain quite high concentrations of these polymeric proanthocyanidins, and this is also worth investigation in the future. But yeah, we cannot do everything, but it would be very interesting to have a look at phenolic compounds in palm fruit in general. I think there are not so many studies out there.
Yeah, maybe there are some antifungal compounds.
Yeah.
Like in Elias guinensis.
Yeah, I suppose also in the seed there are lots of antifungal compounds because the seed will never rot in the soil. It can, I don't know how long it can last in the soil, and it's still able to grow. I suppose quite long. So this is also worth investigating, I think. And also the maybe not just the fruit of palms, also the leaves could be a very interesting source for phenolic compounds for using as biopesticides or in plant protection.
Thank you. Preguntas? No? So we finish now. Muchas gracias por la presentación. Ahora tenemos un café aquí afuera para que pasen y bueno, si tienen preguntas al doctor Steingass las podrían hacer en ese momento también. Muchísimas gracias por asistir.